Hello, Professor. My name is Kumudini, and today I'm presenting Lab 8, which is about inter-process communication using System V message queues. The lab required building a server and 3 clients that all communicate through a single shared message queue, with the server acting as a dispatcher that routes messages between clients. So the setup is a server plus 3 clients, client 1, client 2, and client 3, all connecting to the same message queue. Each client periodically sends a message meant for one of the other 2 clients, but it doesn't send it directly. Instead, every client sends its message to the server, and the server figures out where it actually needs to go and forwards it. It's a hub and spoke design, not a mesh. No client ever talks to another client directly. So let me walk through how it actually works. So here is my directory where I have all the files required. So let's look at our cat server.cpp file. So in my file, the key piece that makes one shared queue possible is ftok, which is this, here ftok. Every process, the server and all 3 clients call this with the exact same arguments. So they all generate the exact same key, and message get function with that key gives everyone a handle to the same underlying queue. That's what lets 4 completely separate processes all read and write to one shared mailbox. Messages carry a M-type field, and that's how routing works without anyone having to write their own parsing logic. Every client sends its outgoing message with M-type 4, which is this is for the server channel. My servers receive thread calls message RCV function filtering specially for M-type 4, so it only ever picks up messages addressed to it, ignoring anything already tagged for a specific client. So once the server has a message, it looks at the dest field inside the message body, which client it's actually meant for, and resends that message back onto the queue. But this time sets M-type to 1, 2, or 3, matching the destination client's number. Each client's own receive thread filters for its own number, so it only ever sees messages meant for them. Because the server has one thread receiving another loop in main function, where's the main function? Okay, it's at the top. So in the while loop, in main function popping messages off to the forward, I used a queue message protected by a pre-pthread mutex t, so the 2 don't step on each other. And for shutdown, pressing Ctrl C on the server sets is running to false, which breaks the write loop. The server then sends a quit message to all 3 clients before joining its own thread and removing the queue. So now let me first set my permissions and create the file ftok needs, then build everything. So let me say chmod +x start client.sh stop.sh. Now we create a server client function that ftok needs, and I build them all. So now that we set make all, now I start the server in one terminal like this. So the server is running. On another terminal, I launch all 3 clients at once, like this. So you can see them exchanging messages continuously, lines like client 1 from client 3, message from client 3, each client only ever printing messages that were actually addressed to it. So to prove that the routing is working correctly and not just dumping everything to every client, I can isolate a single client's traffic. So let me run the server again. But this time when I run my client, I pipe it with grep and only for client 3, for example. So this only shows messages received by client 3, confirming the server's M-type based routing is actually filtering correctly rather than broadcasting. And then back on the server terminal, passing Control-C triggers the shutdown. Each client prints quitting and exits cleanly. So the biggest challenge for me was actually the FTOK key, specifically getting it to resolve to a stable key instead of silently failing. So FTOK doesn't just hash the string server client, you pass it. It actually needs a real file with that exact name to exist on the disk because it uses that file's inode number as part of the key. I didn't realize this at first, so when I ran everything, it looked like it was working. All the clients and the server were still landing on the same queue and messages were flowing correctly. But when I checked with IPCS-Q, I saw the key showing up as 0xFFF, which is what you get when FTOK fails and falls back to returning -1. Every process was failing in exactly the same way, so they all coincidentally ended up on the same broken key, which masked the real problem completely. Once I understood that, the fix was simple. Just create an empty file named server client in the working directory before running anything with touch server client like I did. After that, FTOK returned a proper consistent key based on that file's actual inode, and IPCS-Q showed a normal looking key instead of the fallback value. It was a good reminder that it appears to work isn't the same as it's actually correct. I only caught this because I went and checked the IPC state directly instead of just trusting the output. Overall, I would rate my understanding of this lab as solid. I can explain exactly how M-type is being used for routing, why a mutex is necessary around the shared queue, and how the shutdown sequence avoids leaving zombie clients or an orphaned message queue behind. So to wrap things up, this lab gave me hands-on experience with message queues, thread synchronization with mutexes, and building a proper dispatch pattern. So thank you so much for watching my demonstration. This is the end.